So as we step into today's sessions, I am confident we will continue to gain knowledge that will empower us to bridge the gap between academia and industry in this transformative era. So without further ado, I would now invite Ms. Deepika from HC Polytechnic to introduce our first distinguished speaker of the day, Dr. Harshit Dave sir, Professor at the Department of Mechanical Engineering, SVNIT Surat. So Ms. Deepika, are you there?
Yes, sir. Am I audible?
Yes, you are audible.
So, shall we start, sir?
Yeah, please.
Okay. So, a very good evening to all the respected guests, the respected coordinators of this program, and all the dear participants. I am Dr. Deepika Harbani, currently working as a lecturer in the Department of Mechanical Engineering at RC Technical Institute, Ahmedabad. So let me introduce the first expert for today, Dr. Harshit Dave. He is the professor in the Department of Mechanical Engineering at Sardar Vallabhbhai National Institute of Technology, Surat. He is the Associate Dean, Alumni and Resource Generation, and also Professor in Charge, Research Park and Incubation Center at SVNIT. He had done his PhD in Mechanical Engineering from SVNIT in 2012. Having an enriching experience of more than 18 years, he has worked on 13 research and consultancy projects with a sanction amount of more than a crore. He has guided 8 PhD students and 45 MTech students. His research interest includes additive manufacturing, micro machining, electrodischarge machining, polymer composites, robotics and automation. Dr. Dave has more than 60 publications in international as well as national journals and has participated in more than 70 international as well as national conferences. He has authored 5 book chapters and 3 books. He is also serving as an associate editor in the Progress in Additive Manufacturing, a Springer journal. He is also a member in the Board of Studies of Mechanical Departments at Ganpat University, Mehsana and D.Y. Patil College of Engineering, Pune. Today, Dr. Harshit would share his insights with us on the topic 3D printing of composites. So without further ado, I would now hand over the session to Dr. Dave. Please, sir.
Thank you very much. I appreciate the invitation that is extended to me by Vishwesh sir and Manoj sir. And I also equally thank Dr. Deepika for the nice introduction. Good evening, all friends. And the topic that I would be discussing today would be related to 3D printing of composites. Would it be okay if I keep my camera off during presentation? Today I'm trying from home, so I'm still not sure whether the streaming would remain perfect or not. So without taking any risk, I wish that if I'm allowed, I'll keep my camera off.
Sure, no problem, sir. Please.
I also would like to so is my presentation visible in full screen?
Yes, sir.
Okay.
Yes, sir, it is visible.
Yes, sir, it is visible.
Okay. So good evening, friends. Today I'm going to talk to you about 3D printing of composites. Actually, I wanted to talk about my institute first. I come from a place called Surat. Those who are from far off places across India or probably from out of India, they would at least know the Statue of Unity, which is the tallest man-made statue, and that is situated close to Surat. Surat, as you know, is well known for the diamond and textile industries. Over and above that, there are few very important industries related to heavy engineering situated on the coastline of Surat. We as a National Institute of Technology are are one of the institutes of national importance that is declared by the Parliament of India. We run 11 BTech courses, 20 MTech courses, 3 MSc, and a recent addition is an MBA program. We have about 6,000 residential students on our campus, out of which 1,300 are from mechanical department, being the largest department. We have 55 faculty members in all three domains of mechanical engineering, and we run BTech as well as 5 MTech programs. The content that I wish to discuss today would be around the 3D printing of composites, wherein I would focus on discussing the polymers, metals, and ceramics which are used for printing composites. Some of the case studies I might discuss during the course of the presentation. Finally, I'll come up with some of my understandings about the scope of research, and finally I'll conclude my presentation. We know that 3D printing is a process of joining materials so as to make objects from 3D model data, and we carry out this process by printing the layer upon layer. So even though we print 3D parts, what actually we do is we create a 2D layer at a time. So irrespective of the complexity of the part, we divide that complex part into numerous 2D layers, and we focus on creating a 2D layer at a time. Eventually that group of 2D layers gets converted into a 3D object is a very impressive outcome. We use 3D printing for creating conceptual prototypes. We use them for making tooling parts, usually for investment casting and the allied processes. We also now print functional parts, wherein rapid manufacturing has come up in recent years. This ranges from a small part like a AC vent in our cars to a very large part like the wings of a windmill. Just you can see the size by these images, wherein the size ranges from the size of our palm to the size of few human beings. Of course, you need to assemble those parts, but still each part would be of a size like 1 to 2 meters. Now we know that composites are engineered or naturally occurring materials which come up from two or more constituent materials, wherein they significantly combine various physical and chemical properties, but at the same time remain separate and distinct at the microscopic level. So the advantage is that we do not need to create a third object. We only need to combine two different objects and come up with a combined effect as a composite. Traditionally, composites are made by hand layup technique, wherein we use the fiber mats and place them in a predefined mold, and then use certain resin material to allow it to cure with time. Another addition is the resin transfusion molding process, wherein we may use vacuum to allow the resin to fill up the gap wherein the fiber mats are placed. As far as these two processes are concerned, we understand that when we go for hand layup technique, the larger picture requires a very highly skilled labor. And in spite of being highly skilled person, the task that he does is highly laborious. So often people are not interested in using their skills for such labor-centric process. Similarly, when we go for a process like resin infusion, we require certain very specific devices like vacuum pumps, which increases the cost. 3D printing in a way becomes an alternative manufacturing method wherein we may go for low to medium volumes of production, but it gives us a capability of highly customized parts so that instead of creating a single mold, we may go for creating 3D models and printing the parts. Now, when we come to 3D printing of composites, we largely classify these processes into 4 different categories. At least my discussion would revolve around these 4. One is the fiber reinforced composites, the composites with polymer nanoparticles, the composites with ceramics, and the polymer composites with metal addition. Now, when we talk about the fiber reinforced composites, these are being the most widely investigated and attempted composite parts through 3D printing. So when we try to create fiber reinforced composites, we usually see in literature that there are 4 different processes which are being used. However, the first and last in this list are more attempted. FDM is the most widely used process, followed by SLS, SLA, and LOM process. Now, when we try to manufacture FRC with FDM, it has been observed that the filaments somehow work with a polymer and certain fibers, usually carbon fiber and glass fiber, and they result into an outcome which is a combination of both. So when a part is created with selected polymer and selected fiber, they maintain their distinct identity, be it a continuous fiber, be it a chopped fiber, but it maintains its individuality within the selected polymer. However, when FDM is attempted, we know that nozzle is something which is a very crucial part. Because of the continuous passing of fibers through it, the chances of clogging of these nozzles are observed. Further, it has been reported that when high fiber loading is attempted, the interlayer fusions sometimes weaken, resulting into lower interlaminar strength, because of which often the parts fail. I'll come up with discussion of some of such results. When we try to attempt creating a FRC with SLA process, we know that here there is a liquid resin which is cured with the help of a source of light or even laser. So there is only option wherein we can put up the fibers within the liquid resin. So there people have attempted more study with short fibers or say chopped fibers instead of continuous fibers. Chopped fibers would be like powder, so that can be mixed into the resin, and of course we can go for sonification of it so that it remains evenly suspended into the resin. Or people have also attempted mixing these short fibers over the layer that is to be cured. People have also tried with using fiber mats, but that has not been a very encouraging outcome. So you can either go for pre-mixing or you can disperse the fibers during the process. The third process wherein we can utilize for generation of FRC is the laminated object manufacturing. Here what we may do is we may create a material roll wherein there can be polymers, there can be fibers pre-mixed into the roll, and then later on it can be placed over the surface, and selected part would be created by cutting the surfaces with the help of a source of laser. However, LOM itself is something which is not a preferred process these days, and hence the investigation on creating composites with LOM is also highly restricted. Finally, we use a process called selective laser sintering for creating fiber reinforced composites. Here, short fibers are only preferred. They are created into the form of powders, and they are evenly mixed in certain proportion with the polymer powder. And then this carbon fiber or glass fiber plus polymer, these are spread by the usual rollers along the surface, and its curing is done with the help of a source of laser. So just as the single polymer is being fused with the help of laser, same way this polymer plus fiber mixture is also fused together. Usually polyamides and polystyrene are the thermoplastics which are being investigated by people with SLS. My focus on discussing the fiber reinforced composites would be restricted on FDM based 3D printing. So I'll restrict myself to discussing these processes, the FDM based investigations. There are basically four ways in which composites, specifically fiber reinforced composites, can be created by using FDM process. And I'll discuss all four of them one by one. The first strategy is to use the process wherein the embedding of the fiber is carried out manually within two successive printed layers. So by usual process, what we may attempt to do is print one layer at a time. And after creating one layer, what we may try to do is place the carbon fiber, as you can see in the figure C. These carbon fibers or the selected fibers would be placed manually. Of course, this would be preferred to have continuous fibers. And once these are placed, an upper layer is created over these carbon fibers as shown in D. And after repeating this process, we would get a specific part as shown in the figure E. The investigators have also tried to check what would be the effect of heating, the post-processing of heat treatment on these parts that are created. And this has come up with a very interesting observation. When the part is directly taken for tensile testing after printing, it has been observed that the bond between the fiber and the polymer is weak. So you can see from the figure that at certain particular value of strength, the polymer breaks. Polymer breaks distinctly, and we see that the fibers do not break. They come out from the other portion of the polymer part. So it means that the polymer breaks at its own strength without having any support from the carbon fiber. But however, when this part is put up for post-processing and thermal bonding is carried out, we observe that there is an even mixture between the layers of polymer and the fibers. So when the testing of such part is attempted, we observe that the fibers do not allow the polymers to break. The polymer layers are not broken because they have integrated with the fiber. So this goes on till the fiber loses its strength and the fibers also break. So we see this from the figure B that when the sufficient strength is sufficient load is applied so that the fibers can break, till then the strength of the polymer is extended. So mixing of the carbon fiber into the polymer, even though manually, but with proper thermal heating, gives us a specific type of composite part which shows extended strength of the polymer part because of the bond that it creates with the carbon fiber. This is specific to carbon fiber. There are results available with glass fiber wherein similar type of observation is reported. The second process which we see into the literature is by embedding the fiber prior to the injection. So what it means necessarily is that we create a filament wherein fibers are mixed into the filament. So we need to go for polymer extrusion process. We select a proportion of chopped fibers, say 1%, 5%, 10%, 20%, whatever be it. That percentage of fiber is mixed with the polymer granules, and then they undergo the extrusion process. I'll not go into the extrusion process right now because I'm going to discuss that in detail in the other process. So because of that polymer extrusion, we create a composite filament, and these composite filaments are widely used for creating parts. The process results into very good parts largely because the presence of fibers. This particular is an observation wherein carbon fiber is mixed with ABS in 30% proportion. So when the carbon fiber, chopped carbon fibers are mixed to the proportion of 30% in ABS, we observe that the strength of the part drastically increases. You can see those. Is my cursor visible? I don't know if that is visible or not. So
Yes,
when
yes, it is visible.
yeah, so when we compare the neat ABS with the 30% carbon fiber ABS, we observe that there is a good increase into the strength. And this strength is comparable with the strength of aluminum 6061. So what happens over here, there is a very good observation that when the filament is pre-mixed with carbon fiber, and when these rasters are created, we observe that the interlayer gap, the void that is generated, the size of that void reduces from say 100 microns to 30 microns, because of which the strength of this part increases. Of course, it has to be ensured that the carbon fibers are oriented properly and they are properly dispersed within the filament, so that even proportion of fiber can be observed all across the rasters within different layers of the part. So if we can have the filament which is pre-mixed with carbon fiber as far as this case is concerned, then that results into a good a strong part. The third way of creating the fiber reinforced composites is by embedding the fiber in the nozzle. So what we do is we keep the fiber bundle separate. So somewhere we may have a polymer filament bundle, somewhere else we may have a carbon fiber bundle, but then they are passed through the nozzle together, and the PLA filament is slightly heated up. Of course, that is not having any effect on the carbon fiber. And when they come out from the nozzle, they get deposited on the surface together. So the advantage is I don't need to create a filament pre-mixed with a selected fiber. And the other advantage is I'm able to use a continuous fiber. So when I use a continuous fiber, the entire raster that we create will have one particular thread of this fiber throughout its position. So of course the tensile strength would improve, bending strength will also improve. The improvement in shear strength is not that, but the part that is created would exhibit good tensile and bending strength. So of course here you do not require any specific change into the setup because there is a single nozzle. However, the problem that you face is that we have to maintain proper traction because the materials are totally opposite to each other. So that even distribution would take place only if their traction is maintained well. So the force with which the polymer would come and the fiber would come, that has to be ensured. There is some good part that have been reported wherein no major changes are required. You only need to have two different spools and you need to ensure that they pass through a single nozzle perfectly. The fourth category, which I'm going to discuss slightly in detail, is embedding the fiber directly in the component. So this is the strategy which people have investigated in last 5 years in detail, and even our team of at our lab is also working on this particular strategy. What you do is there is no mixing of fiber and the polymer by creating a filament composite. They do not come out together through a single nozzle. But what happens is there are two separate nozzles and both the nozzles operate independently. One is the nozzle for the filament, as you can see, This is the nozzle for the filament, and the other is the nozzle for carbon fiber. And depending on the design that you have selected, depending on the way you have designed each layer to have the fiber or the polymer, the deposition takes place by these two nozzles. Of course, sometimes extra timing is taken because the two nozzles would not be able to perform together for a smaller part, and hence one nozzle would deposit fiber first and the polymer nozzle would deposit polymer later on. So often this process takes slightly larger time. The work which we have carried out is based on a Mark II 3D printer, which is a very successful model of Markforged USA, and it is meant specifically to use nylon as a polymer, and it has a flexibility to use carbon fiber and glass fiber as a whole. We can see that there are two different nozzles, separate nozzles, one for the polymer, you can see it, one is for the polymer and the other is for the fiber, and they have separate spools which are to be maintained in close proximity to each other. As I said, nylon filament with 1.75 mm diameter is what is used as a polymer filament. The machine uses its own uh, commercially available filament called onyx, wherein nylon is mixed with the selected fiber in certain proportion. As fiber reinforcement, we may use carbon fiber, Kevlar, glass fiber, and these are maintained at a diameter of 0.3 mm. So this is a condition which is fixed. We may not be able to utilize a different type of polymer. We may not be able to use different types of size of this polymer or the fibers. This is a short video that my team has created for showing the setup. So as such, we see that this is a very small setup, a tabletop setup which can be utilized, which can be easily transferred from a place to the other. You can see the lead screws are good enough to take a positional accuracy of 1 micron. This is the feeding mechanism. You can see that through which a fiber as well as the polymer would pass, and they are connected with the head of the nozzle. You can also see that there is a spool of fiber which is placed inside this setup, and because the polymers have detrimental effect of the moisture, so they are kept separately in a box so that they can be properly maintained without the effect of the moisture. There is a build platform which is connected, which is magnetically attached with the stand. So the alignment of this platform is done automatically by the system before the start of the process. Of course, we need to make that selection, and it can be easily separated out so that when you need to remove the part, you can carry the platform away. So that is an advantage of the process, wherein in usual process we see that the build platforms remain fixed. As we saw earlier, these are the two nozzles. One is for the polymer and the other is for the fiber. And each of these polymers and the fiber, they are connected with the feed mechanism, as you can see, that is connected with the proper feed mechanism so that their separate traction can be ensured. Sometimes when you keep 70% of the fiber in a layer, so more fiber has to be deposited than the polymer filament. So for each layer, their speeds would be varied. This is a tricky task wherein you have to connect the fiber initially and you have to pass through it. Often I remember the way my grandfather used to use his hobby sewing machine, wherein that thread has to be passed. The same way manually this connection has to be done. And then we have this dry box. As I discussed earlier, the polymer is placed into the dry box so that we are able to preserve it, we are able to save it from the moisture. Of course, places like Surat, which are more prone to moisture, need this setup without fail. So this is an onyx wherein the nylon polymer is mixed with 1% of the chopped carbon fiber. So this is one such filament that has to be used, and this is the usual setup that comes out. Very simple way of separating the parts at the end, so there is no major issue with the process. When we carry out this, we need to ensure certain process parameters. One such parameter is the orientation. How do we orient the part, whether we place it flat on the surface or on the edge? So we can put it this way or on the short edge. Earlier, if we see the earlier older research papers, we would see that people defining this as X, Y, and Z. But then there were arguments within the research community. So rather than using them as X, Y, and Z, now the orientation is considered as flat on long edge and on short edge. This is how we define. The another important process parameter is the pattern, selected pattern. We may select a triangular pattern, a hexagonal pattern, and a rectangular pattern during the process. So when we select this, we may also have a specific selection for laying the fibers. So earlier I discussed is related to the polymer, but here we are also talking about the fiber. We can orient the fiber either in concentric way. We can put them into one across the other inside out, or we can put them as isotropic way, wherein layers are put up side by side. This can be laid again at 0 degree, 45 and 90 degree. And here it is possible for us to decide the number of external fiber rings, which is defined before the start of the program. So on the outer periphery also we can select to put up 1, 3 or 5 fiber rings, and rest of the portion is filled with our selected design, be it the polymer, be it the fiber. So how do we use the software? Now, one of the issue with the software is that this is cloud-based software, so we cannot install it on our PC. And because of that, whenever you want to use this, the OEM knows what you are doing. So the chances of using another fiber or another make of fiber or the polymer is reduced. So that is one such thing which makes the machine a monopoly machine with the OEM. So we may make a selection of the polymer that we want to work on. Of course, here tool steel is not an option for this machine which we have. We can make the selection of these 4 different types of fibers. Based on that selection, the machine will also be able to identify our selection. We may decide the pattern for the infill, and what density we want to fill, that also we would decide. Based on that, the amount of material that would be utilized is fixed. We may select the number of layers and how many top and bottom layers initially we want for the polymer. So those selections can be made. Fiber layer, number of fiber layers can also be selected, and what way we want to deposit. Sorry. Concentric or isotropic, we can make a selection. How many outer walls do we want to have? That also we can select. And do we have any open space within the part? Do we have some holes into it? That selection also can be made. We can decide the outer rings, and then we can decide at what angle we want to set the fibers, be it 0, 45, 90, whatever it is. So those selections can be made for the reinforcement. After this, we get the details about what dimension we have, how much time it would take, what would be the cost of material, and what would be the weight and the volume of the material that we will be using. It also gives us suggestions for making certain changes into our selection so that we may utilize lesser material or we may make it faster process. Of course, we may or may not agree to these suggestions. So that is up to us. That is what we can do. So by doing this, we may come up across a final part wherein we may have gone for certain basic selection. Now we will be able to view each and every layer. That is the beauty of this software, wherein we are able to examine each layer, and you can see that out of 32 layers, these are different layers, and the software will give us an idea about how the each layer would look like. Now suppose I have made a selection of say 17th layer, and I feel that I want 18, 19 and 20 layers also to be same. So I can create a group of those 4 layers and can copy what is there into the 17th layer into the other layers. So that is also possible, and I can also go for final checks into the program by going through the view of 2D and 3D view of this entire part that we would be creating. So this gives us an idea whether we want to further make any modifications into the program or not. And based on that selection, we can go for final printing of the part. Once this is done, we would go for creating the part, and I wish to demonstrate a flexure part that we have printed for checking the bending property of the part. Initially, we need to heat up the polymer as well as the fiber. We also need to go for heating the build platform, so that the first layer that would be deposited is properly stuck to the build platform. So once that is done, we may make a selection of the part that we can submit through the software itself, which is connected with the machine. So we do not need to have any specific other data storage or data transfer. And the initial setting is done by the machine, its leveling is done by the machine, and it makes initial printing of it initially checks up for us whether the polymer that is selected, whether the fiber that is selected is printed well or not. So you would observe that some first boundary is created with the selected polymer, and then some sort of fiber is deposited for checking, and then once we approve, then the initial part starts getting printed. So once this is being initiated, I'll slightly skip this so that we come across. So you can see those first 2 layers are created, and then the part is being this is the original part now, which is being created, a flexural part that would be created. Some of the layers, I believe that the first few layers are the layers wherein the fiber, the polymer is being deposited. Because this has the chopped carbon fiber, so this polymer appears black in color. And then we are mixing glass fiber, so which appears as white in color. So that would be slightly easier for us to identify. So this process goes on. And there we see that in a particular layer, the glass fiber is getting deposited. So continuous fiber being deposited at a defined place, and you can see that at certain position a triangular infill of the polymer is planned, so that would reduce the weight. Of course, it gives better strength also, and then over that you can again have a full part of polymer and then deposit fibers over it. So eventually all 32 layers are getting printed, and the part is now ready to be separated. So once that is being done, we need to go for removal of the build platform, and slightly careful we need to be so that we do not damage the build platform, and the part can be separated. Of course, you need to go for further post processing depending on what situation we are working on. So this is how this part is being printed. Now the thing is, what I am showing now is one of the layers of this part that we have printed. This is one such layer. You can see that this is as per the software. The white color that you see over here is in the software image. The white color that you see is the polymer, and the orange color that you see is the fiber. Same way, wherever you see the fiber, you see that glass fiber is deposited. There are rings of fiber, so we see the rings of this glass fiber, and then they are laid at 45 degree, and wherever there is small gap, in all that gap again the polymer is deposited. You can see that those polymers are being deposited at those places. So there is the system is able to minutely follow the design that you have instructed it to work with. We have attempted with all three major testing of these parts, and we found that these are very good in strength when you compare it with aluminum. Of course, this is right now under publication, so I haven't shown the results for it. Similar attempt has been made by a big area additive manufacturing system. You can search BAM system in Google and you would get this entire case study. This was developed at Oak Ridge National Laboratory with the support of Cincinnati. And what they have tried to do is they have tried to print very large scale geometries with carbon fiber as a reinforcement with the nylon polymer. And this would give you a full scale of aerospace trim tools which can be utilized as a replacement for metallic parts. Similar observation has been reported by printing the entire body of a car by a startup known as Local Motors. You can see that in this is a large setup wherein this entire model is printed. So there again, carbon fiber provides very good strength to the part, and it has successfully been demonstrated. Of course, we have been attempting creating, because of the limitation of the size, we create some of the parts for the vehicles which our students make for competitions like SAE and Baja. The other category of composites that are being attempted by people are nano composites with selected polymers. So when you talk about nano composites, what we do is you add certain nanoparticles which help us to improve mechanical and thermal properties. And these nanoparticles which are being attempted in recent days are CNT, graphene, some nano ceramic particles, and to some extent now people have started working with metal nanoparticles also. So this can be attempted by creating the filaments which are mixed with these nanoparticles. A large scale research is carried out by mixing graphene, and many good research outcomes have been reported, and they are being utilized. Such parts are being utilized for EMI shielding in satellites, for thermal managements by using them for cooling, by creating soft sensors and robotic parts. Shape memory parts are also created. So graphene in a way is becoming an essential component of 3D printed polymer composites. We also have attempted by creating PLA graphene nanocomposite filament by using our single screw extruder, lab scale single screw extruder system, wherein we mixed the graphene with PLA granules in different proportions, say 1, 3, and 5%, I suppose. And the advantage of these nanoparticles like graphene and CNT is that they are, in spite of being utilized in a very small proportion, they provide very large surface area, because of which they cover the granules very well. And so when they are printed, they come up with a very good, when they are extruded, they come up with a good quality of filament. Of course, this is a tedious process wherein a proper balance of different temperatures, say barrel temperature as well as die temperature, has to be achieved. And once the filament is extruded and passed through the water tank, there also the temperature has to be properly maintained. Without that, we may come up with brittle filaments. So Achieving this particular combination is slightly tricky task, but that is possible. Eventually, we have understood that it can be possible to create filaments with varied quality of its mechanical properties. Of course, once you get a right set of flexibility into the filament, you can utilize it to print different parts. And with our limited exposure to it, we have found that even a very small amount of addition of graphene gives us a comparable result with a neat PLA part. Now the advantage of this is that when we want to reuse the polymer, say polymer parts are crushed and that is being used to create a new filament, it would certainly lose its strength. So even 0.5% or 1% of certain additions, it provides it comparable strength. So that becomes an advantage. Our observation was that once we increase the proportion of graphene, its tensile strength or flexural strength are slightly reduced, but its conductivity improves. So when you want to provide, say, thermal or electrical conductivity to polymers, such nanoparticles become a handy tool for us. People have reported some of these studies wherein people have tried to work with ceramic particles mixed with the polymers. So usually ceramics are very useful in biomedical applications, wherein we require biocompatible parts, where we require very corrosion resistant parts, and at the same time we want them to be flexible. So certain ceramics like titanium oxide, zirconium oxide, aluminum oxide, and calcium ceramics, they can be used, they have been reported to be used as reinforcement materials with different polymer matrix like polyamide, polypropylene, and PLA. These are biocompatible. So you can mix them in a right set of proportion and create. Usually people have attempted to create scaffolds so that they can be utilized and they can mimic the original situation. You can see this. This is the cross section of, I'll pause this for a minute. You can see that this is the bone, and if you see the cross section of this bone, this is how the axial view we see. And what people have attempted is, a group of research have attempted to use PLA plus certain ceramic powder. I'll go into details in some time. And there they have printed here the axial flexibility as well as the longitudinal strength is being attempted, and it is comparable with the natural bone. So you can create a scaffold and you can place it. If a portion of the bone is lost, it is not only cracked but it is fractured to such an extent that it cannot be revived. So such scaffold can be created and placed between the part of the bones, so that especially the hand and the leg bones, if we do not wish to reduce their length, we may place such a scaffold into it, and then we can go for the medical conditions wherein the bone tries to grow by itself. By the time the bone grows, this biocompatible part will keep on getting absorbed by the body, and through various ways it gets removed from the body, and the natural bone grows and takes its place. This is one thing which is being attempted. The other thing is that these parts are created, a scaffold is created, and that scaffold is placed, and in between the bone also grows, and it helps to create a natural bone without losing the length of it. And when these parts were created from, say, ceramic powder, which is hydroxyapatite, and that is mixed with polycaprolactone to create HAPCl. This is what is being found. People have printed it, and axial cyclic compression is attempted. Some compression, removal of compression, again you compress it, and we observe that it can the strain that you observe is comparable with what is required, what flexibility we require to get. Not only that, it is also possible for us to create a part which is flexible enough that you can attempt to try to compress it with the finger, and you can also observe that it is flexible enough to regain its original shape. So this is an attempt for specifically a biomedical application. But apart from that, people also have reported 3D printing of polymer ceramic composites to be used into casting molds, MEMS for making sensors and photonic crystals. You can see the size of these parts. You can see that these are different parts which are attempted by using silicon oxide, uh, by mixing them into resin, so that through SLA you are able to create a part. Here you can see that this is a bioceramic scaffold. You can also see a photonic crystal, hollow turbine blades. You can see the size. Impellers have been attempted, and various micro investment casting molds have also been attempted uh, with uh, with reasonably good accuracy and dimensional as well as form accuracy. So these are different attempts which have been made in recent times by using ceramic particles, mixing ceramic particles into polymer. One of the example we saw that was with PLA, sorry, that was with FDM process, and this one is a case wherein resin is being infused with the ceramic powder in an SLA process. Of course, when we go for FDM process, we observe that ceramic particles will result into enormous wear of the internal nozzle. So what we need to do is we would prefer to go for hardened steel as a nozzle material when we want to print ceramics and metal particles with the composites. So in such cases, instead of brass, which is the most widely preferred nozzle material, we may go for hardened steel so that the life of the nozzle is extended, and the chances of clogging can also be reduced if not avoided. The another category of the parts that we may print would be for polymer metals. Now, when polymer metal is being attempted, SLA does not become a good option because, sorry, SLS does not become a good option because the polymer powder would get fused at certain temperature and metallic powder would get fused at certain another temperature. So SLS is not a good option. Unless you fuse them well, this will not give a good result. Similarly, SLM is not an option because in SLM we need to melt the selected powder particles, be it metal, be it polymer. For polymer, SLM is not preferred because SLS is a better and cost-effective option. Similarly, if we try to go for SLA process where we select polymer resin and we try to mix metal particles, that can be a reasonable option. But because SLA is something which is creating layers to a very small layer thickness comparable to the size of say 10 microns, 20 microns. So the particles that we may require have to be into nano size. So the process becomes slightly costly, and maintaining them at even proportion also becomes a tricky task. So when we talk about metal particles mixed into polymers, we largely observe that people try to go through the FDM route. When we are mixing these two materials, our intention is that we need to focus on properties like adhesiveness, the flexibility, the conductivity, the processability, the toughness and strength. So all these properties which sometimes are good into a polymer and sometimes they are better into metal. So the proportion of mixing metal into the polymer filament would be tricky. So suppose I want to try with say copper metal particles mixed into say PLA filament. Then if I choose a filament which is 30% copper or which has 3% copper, both of them would create a part which would exhibit totally different levels of properties. So the selection of or the requirement of the proportion for a certain application becomes very important. And that is why these filaments which are available into the market, ready-made filaments, are very costly. Because when you create a filament with say 15% of mixing of copper particle, and you try to preserve it for some duration, it is bound to be affected by the atmosphere. So generally such parts are not available readily, and if they are available, they are very costly. Rather than that, going through an extrusion process wherein we mix a certain proportion by ourselves, certain proportion of say copper or steel into the selected polymer granules, and then extruding it and creating our own filaments is an easier task. There are few startups who are doing into it, and based upon your requirement, they fabricate your filament and within few days they give it to you. So that is how the metal is being attempted by mixing into a selected polymer for creating a filament for FDM process. Of course, the nozzle that you use with a say open source FDM machine has to be specifically kept for this part, because once you use it, it does not become useful for neat polymers, because we would observe some sort of wearing inside, and then it may not result into exact 1.75 mm for a usual polymer filament. We have attempted creating some parts with copper addition, wherein 30% of copper is mixed with PLA, and that is being attempted to print a part. It prints very well, and we see that such parts have comparable strength. Of course, very few parts we have printed till now, so we are yet to comment on the strength part of it. But yes, this conducts heat and this conducts electricity well. So wherever a part is required, say for example, you can print a single line of polymer somewhere, and it can act as a heat conducting part, or it can also act as a electric conducting part. So now this opens up a totally different and interesting area of research, wherein you can think of any application wherein you do not want the entire part to be conducting, but a small part of it can be made conducting. So once you connect those two dots, it becomes conducting, and rest of the time it remains insulating material. So that is an option. You can create few layers within by with copper plus PLA filament, and rest of the component throughout the component can be a simple PLA part. So basically it does not conduct through the part, it does not conduct electricity or the heat through it. But in case if you wish to conduct heat or electricity, you only need to connect those portions within this part, and that can result into a useful application. Of course, that is yet to be investigated from our end. People have attempted it for heat exchangers and for micro parts for electronics, but that is very rarely done. So a problem that we face is we do not allow, because the metals or the ceramic particles have very high melting points. So of course we do not cross 150 degrees Celsius when we use polymers like PLA or nylon. So those particles, metallic or ceramic particles, do not come under the effect of the heat, but they affect the viscosity. So the flowability of this filament during the process becomes a critical issue. The way we add surfactants or plasticizers is something which has to be investigated. And say, for example, if I'm able to find a right proportion of a selected plasticizer or a surfactant additive into it, I would make it my trade secret. I'll not share it with someone so that it becomes a viable product for marketing. So there is a scope wherein people can attempt and try to come up with combinations. They can make it open after patents, or they can keep it a trade secret and come up with the filaments. The additives, when they are mixed into this is surf extent or plasticizers, when they are mixed into the polymers along with these metal particles, they affect the viscosity and the part becomes more homogeneous. However, the attempt which has been initiated is restricted to copper or aluminum or iron powders, and there is a wide range of mixtures that can still be investigated. So that is one such area which can be worked on rather than focusing on the printed part. Creating of filaments is something which is a very crucial and important task which we Indians can do. If we can do that, our useful resources which go in importing the ready-made filaments from our neighboring country, that can be reduced. Not only that, our cost estimate is that if we can create these parts, the one filament which spool which we bought for say copper plus PLA, that cost us somewhere around 8,000 rupees. And when we try to create say 250 grams of such filament, roughly that was created in around 1,000 to 1,200 rupees. So there is a drastic possibility of reducing our dependency by creating good quality filaments. Of course, the quality is not comparable to what is available in the market. That is something which has a good potential of investigation. It can help to publish good papers, or it can help us to get good patents, and then that can be converted into a commercially viable products. So this is something which is open for all of us to work on. Another area which is not yet attempted is using natural fibers. If we can reduce the man-made fibers and bring in natural fibers by reinforcing them into composites, we can create environment friendly parts if we are using materials like PLA, which is already biodegradable. So if we can use fibers, natural fibers into it, the problem is when we try to deposit these fibers, when they come into contact with these polymers, they burn. So often that becomes an issue. So that has not yet been a right set of combination. Similarly, as I said, adding metal particles into polymer matrix is something which requires very good scope of research. There are few startups who are working into it. They are supporting some student funded projects so that they get their desired outcome by involving students. So this is something which we can work on, we can utilize, especially in Gujarat. We have good support from the state government through SSIP, so students can take up. Some of our students take such task and they work on it, and that can become a mass movement, so that our dependency, say for example, my own lab procures about 2 lakh rupees of filaments annually for various projects that we work on, be it for the creating composites or our regular 3D printing. So in such a case, just if we make a count, this would be into a few $1 billion industry. If a share of say 5% or 10% also can be brought in into local industry, that is a huge saving of our resources. So these are the possibilities where we can work on. Some of the facilities that we have in our lab is, as I discussed about this machine, we work on PLA, we work on ABS, we work on nylon, we use FDM machines, we use SLA machines. We have created our own ink writing machines. We work on clay 3D printing, wherein we create various ceramic parts. Recent addition is a selective powder deposition setup, wherein we are trying to create metallic parts. We fabricate our own filaments to some extent as far as PLA is concerned. Various blends of polymers we have attempted, though not that successfully, and we are able to create some good nanocomposites with CNT and graphene. So there is a good scope of working on polymers and polymer composites with our research facilities. You can get in touch with us through virtual mode by following us on social media, and ours is Advanced Manufacturing Lab in Department of Mechanical Engineering. If in near or far future when you are visiting Surat, please make it a sure stop for a visit, and let us see if we can discuss and we can interact so that we can work together. We can accommodate 2 to 3 MTech students at a time from other institutes. We can have 5 to 7 interns at a time, looking to the facilities that we have. So you can encourage your students to get in touch with our team and can think of working with us. With this, I come to the end of my presentation. Thank you very much.
Thank you, Dr. Dave sir.
Thank you.
It was a very informative session on the 3D printing of the composites. And I'm glad that some of the participants have come up with a query, sir. So would you spare a few minutes
Yeah,
to?
sure. We can have 5 7 minutes, of course.
Yeah, so I request Dr. SSK to present the query. We'll unmute you so you can directly interact with Dr. Dave.
Deepika madam, I have unmuted all the attendees. So
Yeah,
they can ask. They can unmute it themselves and they can ask their questions.
so I request the participants who have put up the queries in the chat box, you can directly unmute yourself and interact with Dr. Dave, sir.
Good afternoon, sir. Good evening, sir. Dr.
Good
Suresh.
evening.
Yeah. Actually, the particle size will be restricted in a nano size or in micro size also is possible to print it with this composites.
The problem that we might face is that they may create troubles in proper extrusion through the nozzle. And so that is why the particle size has to be restricted to nano size or maybe a few microns only. So we may not go for say 50, 70 microns powder size. The maximum that we have tried is 25 microns with copper. So that has to be restricted, because while extruding and creating a filament also they would restrict. They may harm the internal surface, and while printing also they may clog the nozzle, or they may increase the diameter of the nozzle opening with time. So that is why the particle size has to be restricted. And in fact, that limitation gives us an advantage wherein we create parts which are stronger, which give us better thermal and electrical properties. Because of the smaller size, they give us a larger surface area. So a limitation becomes a strength.
Why I ask is agglomeration is possible in the nanoparticles. That's what, sir.
Yeah, that is possible, and it has happened with us also when we tried with, for the first time when we tried with graphene, that happened, and we could not create parts which could have a proper mixture of this throughout the PLA granules. So later on, we went for proper spreading of this graphene across the surface of the PLA granules, and we also went for smaller size of granules, so that once they melt and once they extrude, that can be avoided.
Thank you, sir. Thank you.
The next question.
Hello, sir. Can you hear me?
Yes, sir.
Hello.
Yes, sir.
Yes, you are audible, sir.
Sir, yes, sir. Sir, can we use the? I'm having a general question actually. Can we use this 3D printing in future for mass production? Because today, if you see, we are using this technology for job production or batch production. whether it is possible to use this technology for mass production in future.
See, the thing is, when we talk about mass production, what we understand is we want to go for more number of parts in the same time frame. So suppose if I'm taking say 60 minutes to print one part, if I'm able to print 4 parts in 60 minutes, that becomes a viable option for mass production. So as far as FDM is concerned, that is not an option. With FDM, we cannot do that. But there is a possibility with process like SLS or SLM or say SLA, wherein if we can reduce the cost of the setup and then can go for larger build platforms, then we can go for a matrix of say 3 by 3 or say 5 by 5 and can print more parts. So with SLA, it is there is a possibility. Of course, we need to go for the lesser and not the DLP one, so that the entire layer can be scanned at a time. Similarly, that can be done with SLM and SLS, but the restriction today is the build platform size. So the size of these platforms in the available machines are too small that we will not be able to go for more number of parts. So to sum up, FDM is not an option. The other processes can become an option, but for that you will have to increase the size of the build platform so that you can print large number of parts at a time. But of course, today that would increase the cost of the machines to an enormous number. I believe once these patents would become free, we Indians only would make larger machines. Thus, just as we have made larger machines in India for FDM, I believe that for the other processes also we will be able to make larger machines. And who knows, there would be people ready to make it, but because of the fear of the patents, they are not yet into the market. But I'm hopeful that would happen through Indian manufacturers someday.
Yes, sir. Thank you, sir.
Yeah, the next question, if any.
Sir, my question is that you said that we can use the composite materials of natural fibers, which we can use it. But what about the coir material where we can use it, sir? Coconut coir.
I'm not
But
getting.
we have coconut coir.
Yes, but in that case, it see the coconut fibers that we can obtain, they have to be chopped well, and then that can be. I believe that should be utilized.
What about
I haven't
the
come across any research, but the thing is, continuous fiber may not be a possibility, but chopped fibers can become a possibility.
Uniform printability is possible in that, sir, or interfacial adhesion?
I fear it may not be possible with the current knowledge that we have.
But
For
only
as far as
FDM is the only technology we can use it for these natural fibers composite material, no, sir.
Yeah, if we can create the filament, it is possible, and to some extent, I believe that we can go for SLA, but there the temperature depends on what resin we select, because it may require a larger amount of heat, and possibility is that natural fibers may burn during that heat. So that is why, because it is not able to sustain higher temperature, so that is why it is not being utilized today. But to some extent, if we can go for some hybridization between the natural and man-made fibers, who knows? I'm not sure. We haven't done
But
that.
some of the articles when I read the applications of this natural fiber or in automotive and aerospace industries also, and also construction and consumer goods. If that is
Right.
to be the case, then we can go with this FDM technology or some other process we can adapt it, sir.
I have come across one research wherein what people have attempted is mixing these fibers, the natural fibers, the coconut fibers and the banana fibers, into concrete, into a
The
selected
construction materials which
yeah,
they prepared in
but
blocks.
then that becomes a free flow extrusion process. It won't be FDM process. So such extrusion can be utilized because we do not require to heat the filament to certain temperature. So yes, when FDM is not an option, but yes, free flow extrusion is an option wherein we can mix natural fibers. People are attempting it, and uh, personally we haven't done it, but we have tried to mix certain polyester
Additional.
fibers with polyester fibers we have attempted mixing into clay and then extruding it. So that is a possibility which we have recently observed, but still we are to venture. We haven't worked with natural fibers, but yes, that is a possibility. We can work on it, and if we can do
And
that, we can create a whole lot of cottage industry wherein people can make chopped fibers, and that can become a small scale MSME industry, and it can be pan India industry because our entire coastline has coconut. We are a huge producer of bananas, so banana fibers can also become, jute can be an option. So, but yes, that has to be investigated in a proper way, yet to be investigated.
right, sir. And one more question, which maybe is
Ji.
silly to you, but you're talking about the Patel statue, which is available there, the Statue of Unity. And
Yes.
there was a saying that it was out of all the waste materials, the brass rods and other things. And those melting points are not available with us. So we imported all those cascading technology and carving technology from China, and we inculcated it. That is what the studies are saying it. Really, we don't have any mechanisms for that, sir.
Uh, of course, no, that is not a silly question, first of all. And the thing
Because
is,
I'm not going in depth
yeah,
into that.
yeah, the
I don't know, sir.
metal was collected from the farmers, and of course it was not used later on. But I have come to know because the chief engineer of this project was our alumni. So when he visited us, I put up the same question to him, and he said that whatever metal was collected, that was used to build. If you go to this statue, there is a gallery, and there small versions of this statue are erected, small like say few feet. So that metal was used to create those replica, and they are placed so that that utilization can be shown. Now, L&T was one of the major partner in building this. So as you said, casting of those small parts. Say for example, if you observe this statue from near proximity, some videos are there. You would see
Yes,
that
sir.
there are small patches. Now those small patches are also very large. We cannot show it by extending our arms. They are larger than that. But those small patches were fitted on a steel structure to give this shape. So those patches, the process through which this was made was outsourced by L&T to some Chinese firms. They had, of course, they worked here, but that technology was with them. And the entire structure, the internal structure that you see over which these are fitted, that was created by L&T.
That was the contribution of some of your alumni in your institution, sir. What is the contribution of our institute towards that
Yeah,
Asian
I
components?
believe that contribution comes from many such institutes because engineers who work with L&T and their subsidiaries, they come from all across India. But what I was saying was that the chief engineer who was supervising this entire project on behalf of government of Gujarat, he happens to be our alumni. So he came and talked about this entire program at our institute some days back, some months back. So
Sir,
that's
when
how I
we
came
are
to know about it.
yes, sir. Yes, sir. When we are talking about the Ramlala temple, also they were telling that people from Gujarat, this institute was coming and they are planning for the material management, which was very
Uh,
interesting to read that article.
yeah,
So
the
that's
thing
what I
is,
asked you, sir.
no, the thing is the exact venue where this temple is erected. Of course, I cannot technically comment on it, but the soil structure was not suitable to create the foundation as per the original plan. So they came up with a team of 8 experts from all across India, and one of the expert was the then director, Professor Gandhi.
That's what I read, sir.
Yes, who served as professor at IIT Madras, and he retired from IIT Madras and continued serving as our director. And he is a man of foundation engineering. So the L&T and SR industries that are set up on the coastline of Surat, that is also, Surat does not have a proper beach because it is totally muddy area. So in that area also the foundation was designed by Professor Gandhi. And in fact, he is instrumental in creating the clay and concrete printing is also coming up, but the clay and ceramic work that we are doing right now,
Structural
he was
design.
instrumental in setting up that part of the laboratory in our lab. So yes, most of the leading engineering institutes, be it into government or be it into private sector, they contribute in nation building because they come up with good alumni who serve various industries, and that is the beauty of India.
So nice, sir. Thank you. Nice. We got an opportunity to talk to you because such a great person you are and your institute is. Thank you for the opportunity.
I appreciate your words, but I don't feel myself worthy to be called great. Hopefully, I would keep your words someday, and I would keep working towards that. Thank you.
Thank you so much, sir. I'm from Shastra University, Tamil Nadu, sir, Tanjavur. I'm
Acha,
not
okay.
a engineer, but I'm teaching material management for people of operation management. So I'm
Acha.
interested in these type of items. I'm working on it in Industry 4.0. We are also
Supply chain,
having 3D
supply chain
machines.
management and material management is going to be a point of research in 3D printing in time to come.
Yes, sir.
Because
That's what I joined.
to make it sustainable and to make it affordable and reusing of the material, even government wants that the concrete should also be reused. So 3D printing is a good option. So material management and even supply chain management has a huge role coming up in 3D printing also.
Sir. Hello,
Hello.
Professor. I am Dr. Sidil Kumar. I have sent
Sir,
three
can you be
questions in chat
slightly
box.
loud? Hello.
3 questions in chat box. I have
Okay.
low network in my village.
Acha,
So
acha.
kindly answer that one.
I request the administrator to read those questions. I don't know. Somehow I'm not seeing the chat box yet. Can
Sure,
I
sir.
stop sharing? Probably I'll then able to go to the chat box. Yeah, which question sir was talking about?
Sir, I think sir wants to ask, can we combine leaves of tree along with clay for 3D printing?
I'm not sure because the thing is you will have to dry the leaves first, and eventually they may get degraded, and they would make the part porous. So depends on what application. If we want some porosity to be created and then that has to be filled with something else later on, maybe it can work. Also, when you make a part,
I'm not asking that question. Hello. The PLA, PP and BA uses for the nanocompost preparation. In which one is suitable for orthopedic application?
which is the question?
Sir, I'll
Professor,
repeat
you
the question.
mentioned.
Can you suggest suitable ceramic if it is for 3D printing? Which composition is good? PLA ceramic, PA ceramic, or PP ceramic?
PLA is something which has not that been widely, but PA is something which people have worked. Personally, I haven't yet worked with polymer plus ceramic, but more literature you can see on PA rather than PLA.
Oh.
Okay.
So one more
Answer.
question, Professor. And 3D printing, nano compost preparation, which 3D printing is suitable? Can I buy that? Which type of machine? For example, I am using a ceramic material with nano compost preparation. Means which one is best in Indian market? Which 3D printing we need to buy in our university like that?
Actually, when you want to mix nano ceramic particles, you can use any open source 3D printer. So I would suggest that go with the cheapest machine. Say one machine which costs you 70,000, 1 lakh, 1 lakh 25,000. Go for such machine, play with that machine, and create a proper understanding of it, and then go for a large scale machine. But of course, it should be open source machine, be it FDM or be it SLA. So rather than investing say few lakhs, like say 20, 30, 50 lakhs for getting a polymer SLS machine and then not able to do it well, I would suggest that go for a regular open source FDM or SLA process. Play with it, try with it. Even if the machine, one of my SLA has failed by trying mixing two different resins together. 1.5 lakhs machine we have just lost because of that attempts, but it's fine. That is something which an institute can bear. But if we go for a large scale machine like SLS or SLM, and then when we are not able to do it, so there are no specific machines which are available wherein nano composites can be created. We have to use an existing machine only to do that. Now the tricky thing comes when you think of FDM process. When you want to work with FDM, their filament is a tricky thing. So say for example, the one which we have, say Markforged machine. So there our limitation is because it is a open source machine. Sorry, it is not an open source machine. So I'm not able to change the fiber that I'm using. I'm not able to change the polymer that I'm using.
The
So
tip
I am
also
limited.
problem.
Yeah, so that is a problem. So if I want to go for a ready-made filament which has fiber into it, then I need a good quality extruder which will help me to create a filament. I would suggest you search for a startup based in Belgaum,
Okay,
Karnataka.
Professor. Oh, thank
Delta
you.
Sys. Search for Delta Sys. You will
Delta
find
sys.
it Google. Yes.
Thank you,
That
Professor.
guy.
Another one important question, Professor. We are mixing with PLA and ceramic, PA and ceramics, or PP and ceramics. We tried a lot of composition. So in your experience, which type of mixing is best? 50-50 or 70-30, 80-20 like that. If you give some suggestion, means we can use that one.
My own experience with say metal powder is up to 20%. 30% is not a good result. And as far as ceramics that I have referred, there also the usual proportion is up to 15-20%. As we go on increasing the proportion, what happens is the part starts becoming brittle. The molecules of polymers are not able to remain attached with each other because they do not create an alloy. Unless and until you create an alloy, they become a single entity. So because of more number of metallic or ceramic particles into it, those polymer chains that have to be developed, they become brittle because they are not able to sustain for a longer length. So such filaments usually with time they become brittle. Sometimes they become brittle in 3 hours. That is my observation. Sometimes they become brittle in 3 days or a week's time. So proportion as far as possible, if we keep it lower and come up with a better option, then that would be a nice.
You shown one orthopedic bone using with the graphene plus some PLA or PPA. Like that, I am using in ceramic means I can get better with the 20 and 80. First, I will try to 20 and 80 and go for 70 and 30 like that.
Yeah. But you try with smaller proportions and then go on increasing. So what happens is, say for example, 1%, 3%, 5%, you observe that the quality improves, the strength improves at 5. and then you try 7. At 7, if you observe that it is reducing, also try 8 and 9. Again, if it keeps on reducing, then there is no point in moving beyond 5 or say 6 or 7.
Okay, Professor. Thank you.
But if you try with, because these powders are very costly.
Yes, Professor. The ceramic zirconium oxide is very costly.
Yeah. So if you try with higher proportion and if it fails, then it fails is also a good finding. But the thing is, we'll not be able to publish it well.
Yes, Professor. I'm also facing same problem. That's why I'm asking. Thank you, Professor. Thank you.
Deepika, you please.
Deepika,
you are mute. You are muted. Deepika, you are muted.
Yeah. Thank you, the participants, for putting up the queries, and I thank Dr. Dave sir again for such informative session and for your engaging videos.
Thank you. My pleasure.
Yeah.
Thanks to my student team. I haven't done anything into it, just used it.
Thank you, sir. And now, before
Thank you, Dr.
moving...
Rashid.
Thank you, sir. Thank you very much.
Thank you, Arshad sir. Thank you so much.
Thank you. Thank
Sir,
you. Thank you.
Sir, kindly share your mail because the last slide is immediately came. I didn't note it.
I'll just type it in the chat box.
Okay. Thank you, sir.
So before moving to the next session, I would request all the participants to please switch on their camera so we can click some common photographs for today's program. So I request all the participants to please switch on their camera.
Fine. Probably we can move to the next. Thank you, Dr. Harshit, for sparing your valuable time.
Thank you. Thank you very much. I'll take your leave, sir.
Sure. Thank you.
Thank you, sir.
Bye. Bye.
So now it is the time for the introduction of the second expert speaker for today's program, Mr. Nimesh Chenoy. He is the Director, Sigma Weld Electronic Devices Worldwide Private Limited. Talking about his academic background, he has a double degree in computer science and computer systems engineering from Royal Melbourne Institute of Technology, Australia, and a PGDM in family managed business from SP Jain Institute of Management and Research. His experience in the welding sector comprises of about 4 years in the research and development and 17 years in the project sales and marketing. He is the Honorable Secretary of the Association of Welding Products Manufacturers of India, IIW Central Council and Mumbai branch representative, and also a member of Electrotechnical Division of Bureau of Indian Standards. Having contributed to numerous projects of national significance, one of which included the indigenous development of the welding solution of the solid fuel booster used in Chandrayaan 2 and 3. He has about 35 publications, including the journals, seminars, conferences, and the reports. His expertise in the field of welding science and technology has led to many innovative and unique solutions to the industrial problems. He has many awards and honors in his name, one of which is the winner of the Dynamic Young Entrepreneur from WeldFab Tech Time. So today he is with us to share his views on the topic demystifying implementation of Industry 4.0 for welding in manufacturing setup. I'm sure that now we cannot wait more to hear him out. So let me quickly hand over the session to him. Please, sir.
Thank you so much for the lovely introduction. And I must say, stepping in after Dr. Dave's lecture seems like a tough task because I only could join 15-20 minutes ago. I could see the number of questions. So two very encouraging things. One, that people are attentive, they are listening to what he's saying, and there are lots and lots of questions. And in fact, I was feeling sad that I joined very late. I could have attended his lecture. Somehow I'll see if that's possible later. But thank you for this warm welcome, and thank you the team for having me on board. I believe this is a 2-day session on this topic. This topic we can stretch as much as we want, but what I will do is I will split it into two halves. The first half today that we'll cover as far as possible would be from the beginning of what IoT stands for, or Internet of Things, or Industry 4.0, and we'll try and understand how it has always been around and what is it. And then we will move slowly into the domain of welding and why do we need it in welding. And then maybe today, tomorrow, we will also see how to execute it on different shop floors at different configurations. So if that's okay, I can start the session.
Sure, sir.
Okay, I'm just going to share my screen. And if I can get a very quick thumbs up from you guys that my screen is visible. Is that visible?
Yes, sir. Your screen is visible.
Now it is visible, sir. Yes.
Okay. So are you seeing it, the slide change? You should see a slide saying about me.
Yes, sir. Right.
Fantastic. Thank you. And they've already introduced me, so it's a little bit about me. My name is Nimesh Chenoy, and I represent Sigma Weld at various forums. The company Electronic Devices, where we are, is about 50 years old. We have more than 287 employees. We have exports to more than 80 countries and 10,000 plus customers globally. Few of the contributions that we made were to do with solutions for Chandrayaan 1 and 2, the heat treatment procedure for Gaganyaan, which is going to be launched now. India has 6 nuclear submarines. The titanium bundle weldings and the end pin PWHT procedure was developed by us for that. Lots of photo bridges for the defense, safes and locks that you see every day by Godrej. Some nuclear and shield welding, which was critical, developed for NPCIL and Godrej. And there was a very good thing that we were able to achieve was the internal bowl orbital tick welding process developed for PFBR, which is the Bhavini project, and it was used to solve a critical problem there. Few of the awards that we were awarded, one of them that we are very particularly proud of was the National Technology Award in 2023, which was awarded in the MSME category to us. Now, coming back to industrial revolution so far and what has happened. The first industrial revolution was the steam and mechanical system where it all started, getting things mechanized, steam used to drive motion. That was the beginning of how things could be used, how machines could be used to start helping mankind in making things easy for them. The second interesting revolution was the generation of electricity, the assembly line, and the birth of mass production, and how things could have been produced bigger, better, faster. This was all with the help of electricity coming into play. The third bigger revolution was computers, the beginning of automation, semi-automatic, hard automation, robotics, and things like that. And I have seen through the 90s when I was studying, late 90s, early 2000s in Australia, Melbourne. Now Google seems to be a very common thing, but back then Google was also just a startup, and it was amazing to see how computing could lead to many, many things. And I'll share some of my examples from back in the day, which led towards AI or automation and how it is existing even today. And the latest and the most buzzword nowadays is Industry 4.0, which is computers and automation when come together in an entirely new way, with machine learning algorithms that can learn and control robotic devices with very little input from human operators. This is the crux of Industry 4.0. Now, before there was IoT or Industry 4.0, I think these are few things that you've always known. And, there were things which were GPS-based systems, so that track location, speed, and the black box. So if you ever flew in an aeroplane since the mid 60s or 70s, they always had a black box on it, which could tell you all the data that was of the flight was recorded on the black box. It is still date and practice that exists. So that black box has been around for ages. It has been collecting this data. After that, if you look at AI and machine learning, now many examples of machine learning exist since the early 80s and 90s. And AI became a part of this since 90s, if you could know what neural networks were. And this is how they started, collaborative learning, where you could write algorithms which could actually understand a part of the overall system and work how your brain works. So if you took a big image, fed it to this algorithm, it would understand the whole image, break it down into pixel ones and zeros and the sequences. Then you could crop a small part of the image and feed it back into this database. It would throw the big image back at you. That means if somebody was trying to break a copyright by copying an image, today you can very easily analyze it through a neural network and it can tell you whether this image was copied or it was original. Similarly, there was SCADA, which is supervisory control and data acquisition. This has been around for a very long time. So in shop floors, you have multiple machines working together. They were all communicating with each other using SCADA. That means there would be a central PLC or a SCADA-based software which would monitor supervisory control on all the parts of the line. It would collect all the data and then it would take control as and when required to start or stop a production line. This was what SCADA already existed. Early 1990s, when mobiles were not so popular, especially the smartphones that we see today, Compaq had a device called iPack. It is a palm top device. It came with a possibility of a SIM card, and it had the ability to do computing. So back in 1999, we made the first IoT based device, you could call it, wherein uh, on this device you could log into the web server, and at the back end in the shop floor you may have a store which would tell you what is the inventory for each article. And if a salesman went to take an order from the customer, he could very well see the live status of the store and book the order accordingly. When I talk about this today, it seems like a very simple thing that's possible. But back in 99, imagine there was no consistent internet, forget 5G, there was not even edge available at that time. And you had very little data, which was SMS based, which was traveling between servers, and internet was still taking shape. There were not enough nodes for you to transfer the data. So this sort of data that could go through GSM and could be collected and seen was very good. Later, this idea was picked up by DHL and they started having sign-offs on the parcels that they delivered to the customer on the PDA. This gave a confirmation back onto the control server that said, okay, this parcel has been tracked down to the end of line delivery. So these were early implementations of what IoT was doing. If you have ever traveled on a taxi nowadays, the taxi guy usually doesn't drive over a particular speed limit. That is because a device called governor is installed in the car, which gives SMS to the owner that the car is going beyond a particular speed, and then the owner could have challenged the driver that you are not supposed to go over 60 or 80 to maintain the fuel efficiency. Why are you going at higher speeds? So governor is a device which was put in place long ago. You all have seen smart homes and offices where ACs, microwaves, washing machines, fridge can be operated from your mobile phones. More interestingly, now there are fridge which you can log into your Amazon account. The fridge takes a check of what all you have put inside the fridge. When you take something away from the fridge notices it and it will reorder for you automatically from your Amazon account. So you did not order, but it will reorder for you. And then there is Google Assistant, which today can do anything for you practically. If you ask Google, assistant on your smartphone to book a table at a restaurant, it will negotiate with the table for a table for so many people with a restaurant, and the people at the restaurant wouldn't know whether it's a human or a computer talking to them. Google Maps is another classic example of where real-time data is shared. If you mention that your car has had an accident on a road and report it on Google Maps, all other drivers can live see that there is an accident that has happened and a block that is happening. These are real-time examples of what you see IoT on a day-to-day basis. The Mumbai Police traffic system also now works on IoT. So they capture data from the camera if you cross the line, if you break a signal, and they send that photograph on your registered mobile number to the car as you have to pay the fine. And this is the reason why. So that's how far IoT has gone. Now the question is, you can collect a lot of data, the big data, and whatever you collect, you process will be processed accordingly. So if you collected junk data, you will get junk analysis out. So it is very important to know what data to collect. Just because you have infinite storage, you cannot keep collecting all kinds of data. You would collect what to collect is very important. How much to collect is also important. So in terms of welding, for example, if you wanted to capture the welding current data, how frequently you should capture that data? Would you capture it every 10 milliseconds? Should you capture every second? Should you capture every 10 seconds? Should you capture every minute? It will depend totally on the process and the criticality of the process that you want to monitor. But how much to collect is important. And then, of course, when to collect. There must be a trigger which says this is when you should collect the data. Now, how to use and analyze this data very effectively is also very important. I'll just share a very quick example. We had supplied a SCADA system to Mahindra and Mahindra. And this SCADA system was the first SCADA system working on a forging machine line. So if you know what a forging machine is, you put raw material, that is billets, iron billets inside. It will preheat, it will heat up the billets up to 1200 degrees or forging temperature, push it out to the press, and the press will forge it to a given part shape that you want. And Mahindra always had a complaint that, the machines are not working at 100% efficiency. The downtime is very high. So we had installed a SCADA onto the system, which would got sensors everywhere, and every alarm had a legible meaning. It did not say alarm B4. It would say alarm is billets missing or no billet to heat, for example. So you know that, okay, there are no billets. If there was a problem in the machine, it would say generator fault, it would say VMF, voltage medium frequency fault, etc. They were all textual data. So after 2-3 months of installation, we had a meeting in which the Mahindra team told us the machine is down for 29% of the time. How can we use this, etc., etc. So I said, very good, let's see the data. So they pulled out their register from maintenance and started discussing. I said, but why are we using this? We have a SCADA system. Why don't we use that data? So we both went to the machine, put in the USB drive, downloaded the data, came back to the meeting, plugged into the system, and we saw, okay, even the machine shows 29% downtime and your register shows 29% downtime. So that's very good. Why is there 29% downtime as per your register? And they said, we don't have exact reasons, but it is down from so and so many days in the night shift. So we checked the data in the SCADA, which says you have got 28% of the times the same error, and that also is only in the night shift. That also starts between 1:30 and it resolves at 4 in the morning. So we said, what is that error? The error is there are no billets. So the night operator did not load the billets. He went and slept at 1:30. He came back at 4:30, restarted the billets, and machine was working okay. In terms of the maintenance guy, the machine is down. In terms of the production or the manager, the machine is not working. Whereas the fact was the operator was not putting the billets in. With the help of SCADA and the right data collected, which said this is the error, when they analyzed it, they realized that there is only a reason for us to check whether the operator is loading the billet or not. And then there was not more than 1%, 2% breakdown time. So if you use data and you collect it and analyze it in the right way, it will be more fruitful for the purpose that you want to use it for. Today, why is the manufacturing industry spending billions on IoT? It offers very rapid return on investments because it improves efficiency, it helps automation, it helps become customer centric, and it increases competitiveness. All of you that have used any sort of online platform to order a parcel, whether it is Swiggy, Zomato, or any courier that you have ordered from Amazon or through India Post also today, you get a tracking number. And through that tracking number, you can check where your parcel is given at any given point in time. This kind of customer centricity is what can be done when the data is collected, analyzed, and given. So if there is any kind of delay, you know it beforehand. If there is any kind of timely action to be taken, you know it beforehand. This is Internet of Things in a manufacturing plant in general. So any manufacturing plant you see has got raw material that comes in, any kind of process that is done on that, and then that processed part is later shipped out to the end user, and the end user knows that they have to clear it. So from the manufacturing plant, rather from the order that comes in is logged into the manufacturing plant directly. The manufacturing plant operator knows that this is the next that is going to be produced in line. The raw material is issued according to that directly, and then that raw material is processed and packed. I have visited the Dell factory in Chennai in the past, and I can tell you that this is exactly how it works. If you place an order online for a Dell computer with a particular configuration, that data is logged onto the system. The system is accessed directly by the factory manager. The manager automatically, the line issues those many components from an automated bin. Those parts are kept into a bucket, and the bucket flows onto a conveyor line with a printout of what is the configuration required. It will go to the particular operator. The operator will insert the particular parts required in the order. From there, it goes on to an automatic testing line which installs software, cross checks whether the software installation has any problem or not. If everything is okay, the report is generated, calibrated, and uploaded online. One print is kept onto the desk, and that goes to the packing area where it is packed, barcoded, and dispatched to the end user. When the customer receives it, he registers the product online, and then the 360-degree completion of the system happens. This kind of system is where complete IoT is in use all the time at all levels. Now, what has helped IoT become more popular nowadays is because the rate of the internet has gone down. So data services are easier. There is a wider reach across the country today. I believe right now we were discussing and somebody asked a question. He said, in my village, there is less connectivity. But even there is connectivity of internet to the last mile today to a large extent where we are able to connect. Now, this means we are able to collect some kind of a data from there. There is also a lot of growth. Need for growth faster means you need more data. If you have data and you analyze, you can use the same resources better. Okay. We will see this in terms of welding, what it means soon after. Lastly, it increases your competitiveness. If everybody today is at the same level, whom will you choose? One who is more customer centric. If you are able to contribute to the customer better, give him a better service, better on-time delivery and information, then the customer would want to stick to your company or your product. Let's come to welding now. How does IoT fit in with welding? When you are welding, what is very important? It is important that you are doing the welding with the right material. The person who is welding is qualified to do that particular welding job. And whatever welding they are doing as per plan. WPS is welding procedure that you have already qualified. So they are welding as per that, which takes care of the heat input, and other aspects. So if a welder wants to weld faster, they will increase the current and weld faster. When they do that, then the metallurgical changes in the part will be higher. That means the grain size will be higher, higher chances of cracking under stress. So it's important that whatever was the set parameters, the welder welds at those parameters. Now we are talking very generic, but imagine the same technology is used and the same welder is used to weld railway bogies, which carries human lives, is used to weld cars, which carries human lives, two-wheelers that you ride on, also the power plants that generate your energy, also the railings that you hold as a support or safety. Everywhere you look at two metals being joined, there is welding. Now, each one of them has to play a critical role. So wherever there is the right sort of weld joint will ensure longevity and safety for all. And if there are repairs, then repairs, what is the cost of repair? Anytime there is a repair, you have to take it off the line, go away, do some process to remove what was badly welded. Then you have to regrind, re-prepare the edges, re-prepare the joint, re-weld. After welding, you have to again check if it meets all your criteria, and then you can salvage that job. So, repairs are always more expensive than making it right the first time. So how can we, save repairs, or how can we reduce the time taken to chances for us to do repairs? So it requires time, money, and possibility. So what is the cost of repair? You have to take in case the planning of the rework procedure. You have to take in consideration the time required to move the faulty part to the repair location. You have to take in consideration time to transfer the welder from one location to another, arc gouging or grinding that particular part. Then some kind of heat treatment may be required. Then you do the repair welding. After you have done the repair welding, re-inspection by an independent third party needs to be done and it has to be reported. Now, if you look at this procedure, this is the cost at each one of the levels for a repair. Now, why did we get into the repair in the first place? Either the parameters were not right, the current voltage that we were welding at, the gas flow was not correct, the heat input that was meant to be on the part was incorrect, or the consumable used for the welding was not correct, or the welder who was welding did not know how to weld it. So if he's a new, not qualified welder trying to do a critical job, that would also create a problem. So with all these things in place, how do we look at avoiding repairs altogether? So any weld joint, you can look at that weld joint from a customer's perspective, a maintenance perspective, a quality perspective, production perspective, and management perspective. What do I mean by this? For any weld joint, what does the customer want? He wants to be sure that the job has been welded with the right set of consumables. If he paid for two stainless steel 304 plates to be joined together, it must be 304 plates. The consumable used must be of the same grade or higher. The job has been welded with the approved WPS. Whatever the welding procedure was set, it is as welded as per that. That's what the customer wants to know. And if there are any deviations, that means that for some reason you had to, increase or decrease the current or voltage or the parameters. What were those deviations? Why were they taken? And what impact will it have on the result, if any? This is what the customer would like to know. And was the welder qualified to do the job? This is the last but not the least. It's important for us to know who did the job. From a management's point of view, they would want to know how fast can we turn this job around. That means if we have something on the shop floor, how quickly can it go out the door so that the money can come in? What resources would be needed to do this job? Do I have enough resources? And how can I ensure the first time right welding of this particular part? This is what the management's perspective is. For the production manager, he wants to ensure the lowest cost of production. That means it is done at the right time with the right quality and with the least amount of resources. He should not have to spend more money on resources to do the job. Also, the production manager wants to know if I employed a manpower, how many man hours of working I had versus how much did he arc. So if I have a welder, I'm paying a welder for 24 days, 25 days of working in a month. It means he's being paid for 400 minutes a day into 25 days. So 10,000 minutes of arcing is what is possible by that welder, out of which how much time is he actually welding. Similarly, for machine point of view, if you had machines on the shop floor that could do welding, how many arc hours does each machine have? And what is the utilization at the end of the uh, day? So if you look at it from a point of view that if I had 10 machines and I have a new job coming in, how do I decide whether I need to buy more machines to complete this job, or will I be able to use the same number of machines to finish the job? I'll need data which would tell me how long my machines are being used today. Consumable usage versus wastage. If you issued 100 kgs of consumable to be put onto the weld joint, how many kgs of those were put onto the weld joint and how many were wasted? So how do you evaluate wastage, right? The stub end losses at the end of the welding in TIG welding or in arc welding, or if you do MIG welding, every time the welder starts, stops, he cuts off a certain amount of consumable to get the welding started again. So how much of that wastage has happened? How do you know? And then right welder for the right job. That means if there is a certification for the welder and he's doing a critical job, you want that right welder to be doing that job. So there must be a welder profile that says this welder has been tested for 5G, 6G, 3G, and he's certified for it, and he's doing this job. This is what the production manager wants to know from any system or for a weld joint. If you look at the maintenance team, they want to know breakdown data on each machine, right? How much uptime versus downtime is there? What kind of preventive maintenance updates, if any, I need to take care, right? So that I can have maximum uptime. Maintenance, as we all know, is almost a thankless job. If the machine is working well, the production guy gets the credit. But if the machine remains down for a longer period of time, then the maintenance guy gets the blame for it. But his job is to make sure there is least downtime. So if there is preventive maintenance, which says this belt was supposed to run 10,000 hours, 8,000 hours or 9,000 hours have already gone by, please go check the health of the belt and replace if needed. If somebody can give these timely reminders to the team, then they will be able to take action in time, check if there is more wear and tear, and replace it on time. AI analytics on the data collected. So if example, a machine was running over temperature repeatedly, what can be the reasons? Is it starving for air? Is it placed properly? That means airflow is correct or not? Is the fan working as per specification? So if the fan is placed, is the fan working as per specification? Or is the machine working above its specified duty cycle? One of these three can be the reasons. So if the machine comes over temperature repeatedly, then there can be a message that pops up to the maintenance team and says, this machine has been, showing over temperature error for the last 7 days. Can you check if it is placed properly? Can you check if the fan is working? Can you check if the machine is working as per the specified duty cycle? Then it makes it very easy for the maintenance guy to find the root cause for the failure that is coming repeatedly. But if there is no data available for them to analyze, then they will only go find out each time what was wrong, correct it, and move out. That fault may come again. So what is IoT for welding? The dream machine is you can scan the job. That means you scan a particular part which is to be welded and you say, okay, this particular part is to be welded. You scan the consumable which you are going to weld with. You say, these are the consumables I am welding with. You scan the welder's card, or the welder scans a card which says, okay, he is the particular welder. The system will automatically get the data from the server, validate the data. Yes, these three are good to go, and then allow the welder to start welding without having him to change any parameters. This is what any production guy would dream of. This is what I want. What is a lean machine, or what is that is something that is possible very quickly, is that you can measure the data. What is the welder welding at? What was the current he was welding at? What was the voltage he was welding at? You can measure the wire feed rate in terms of MIG welding or cold wire feeders in TIG welding. You can measure the gas flow rates. What was the gas flow available at that time? You can measure the wire size, whether he was welding with 1.2, 0.8, 1.6. But what was the welding speed at which it was welding, rate of welding? And this can help you calculate the heat input. And if there was preheating was mandatory, what is the preheating temperature and interpass temperature? If the material is sensitive, they will ask that the interpass temperature must be maintained between 120 to 150 degrees. Then you can measure the temperature, and if it goes beyond that, you can give an alarm saying the temperature is too high, don't allow to weld. Similarly, you can infer or calculate on the go what is the arcing time, that is actual welding time. So every time you weld, your welding current will go up, your welding voltage will change from the OCV, and you will consume some energy from the line. So considering these three combinations together, you can start a timer, and that timer is your arcing time. What is the heat input? Heat input is basically your the current times voltage divided by the speed at which you are moving. So there's a formula around it. It will tell you how much heat input you put onto the job. Okay, if the heat input is very high, it can lead to distortion, and sometimes it can even harm the weldability of the material. If the heat input is right or low, you will have lower distortion and you can have longer welds. What is the weld deposition rate? How many kgs per hour were you able to deposit the material? And what is the material consumed versus deposited? That means if you welded for 4 hours, did you deposit 2.4 kgs? You deposited 3 kgs. How much material did you consume? You can calculate that on the basis of the measured data. And for the layman, this can act as an expert system. So if somebody doesn't know or how to calculate heat input, this could give you the inferred data directly. What IoT can do for you for manual systems that you're using for manual welding, you can monitor and record the welding parameters. That means you could measure the welding current, welding voltage, gas flow, wire feed rate. These are basic welding parameters. You could calculate the arc time. How long was the welder welding? The equipment was on, arcing for how long? You would keep a user log. That means which welder was welding at what time, with what parameters. Once you have this data, you can also evaluate or calculate the weld deposit. If you know what wire size was being used, for example, in MIG welding, if you're doing 1.2 solid wire, stainless steel or carbon steel, you have a particular density. You welded it at this speed for 10 minutes. So you fed that material for 10 minutes at this particular speed. This is the amount of wire you consumed. You know the mass, you can calculate and you can figure out the weld deposit that you had. Similarly, resource optimization. That means if you know I have 10 machines, but these 3 machines were not being used at all throughout the day, my arcing time is only 5%, then I can use these resources for other things. Right? If the system was automated, that means the system was working on a SPM or a robotic system, you can have extended welding parameters, which would mean your movements of the torch or the job, rotation speed, travel speed, all this data you could capture if it was an automated system. How do you capture that? You capture it through the motor, you use an encoder or something to give you the data from there, or you could calculate the data directly from the PLC. Then the welding procedure that the welder supervisor has set and put onto the server could be pulled out directly from the server and fed it to the automation system. So if you said, I'm going to join these 2 materials that you wanted today, then it will go to the server, pick up the job number, the joint number, the welding current voltage it is supposed to weld at, the welding speed it is supposed to weld at, and it will start welding at those parameters only. You can also control the weld output. You can say in an automation that it will not go above and beyond this particular range, so it will not allow it to go. You can calculate heat input, because once you have speed, you can have heat input in place. You can calculate material deposition rate, how many kgs per hour you did, or how many, how much material was used per job. And you can evaluate the total cost of manufacturing. When you look at systems such as automobile industries and others, they are more interested to know what is the total cost of my manufacturing. That means how much line energy was consumed, how much gas was consumed, how much material was consumed, and how much manpower was consumed. So these four data, when they get, they can club it together and say, this is my total cost of manufacturing. So if you look at implementation of IoT, it can be done in three phases. First phase is when you collect the data and you analyze the data. That means we collected the welding current, welding voltage, then we analyze this data in various formats, and then we share the analysis with the customer. Second is you correlate this analyzed data with the WPS, the welding procedure, and you can give alerts on deviations. That means you are not supposed to weld, above 150 or below 100. If you did go beyond this range, the system should raise an alarm and say this was wrong. It was done at so and so time by so and so person. Please check. Third is complete control. That means you control the power source and you avoid deviations altogether. So if the operator had selected a job, it would say, okay, this job is to be welded between 100 to 150. It will set it at 150 and it will not allow it to go below 100. Below 100, it will stop welding. It will not allow. If it says the gas flow should be 8 liters per minute, and for whatever reason the gas finishes and you have no flow or lower flow at 6 LPM, then it will stop welding. It will not allow you to make the mistake that goes into repair. It will stop and give you an alarm saying incorrect gas flow. You must check and see what is happening. If possible, if you're using something like a mass flow controller, you can auto regulate the gas flow to achieve the correct gas flow. And if it doesn't reach there, then you can stop the welding altogether. So there is no fault. Now, as we discuss this for general applications, whatever data, as we said, you measure, it must be smart. It must be specific, measurable, actionable, relevant, and time related, so that it is something that you can specify, measure, and take action, whatever it does. Now, how do we implement it on any shop floor? On a single machine, we can do it. We can do it on multiple machines, and we can do it on site. That means you can have this working at multiple ways. Now, this we covered before, but let's reanalyze this. Why would you want to get into Industry 4.0 or spend some time? At this stage, I would like to take any questions you have till now, because after this, we'll jump more into welding and specifics. So, are there any questions as of now?
No, sir. No participant has posted any query till now.
Okay. All right. No problem. Then we'll move on. Yeah. So the screen is still visible now?
Yes, sir, it is visible.
Okay. So we look at IoT and Industry 4. Why do you, if you spend time and resources in weld repair and rework, then you may want.
Excuse me, sir.
Yeah?
Sorry, sir, for interrupting you, but one question has been posted just now.
Yeah. Which tool are we using for data analysis? So depending on the kind of data, we can use the tools. So we have specifically, you can create your own server database management server systems. So you use something like databases to create the data first, and then analysis can be done using BI or specific queries using SQL. I hope that answers the question. Okay.
Right, sir. And no other query now.
Okay. So then I'll jump back into the presentation. So again, the reasons why you want Industry 4.0 is if you are spending time and resources in weld repair or rework, then you are not sure whether the WPS was followed. So if you want to ensure that, you should have an IoT based system to capture that data. Do you have more post welding process? So if you are using a lot of spatter cleaning, so you have another person only sitting there to clean spatter, to regrind, repair, etc., which means that the desired parameters were not followed. So you must have something that checks that for you. And are you aware about your resource utilization? So if you have a bigger shop floor and you have got more than 2, 3, 4 machines, then you must know whether the welding equipment arcing time is as per what you wanted, how much, because you paid for it. So sorry, whether it is giving you accurate utility on your equipment, whether the welders are having enough arcing time. So if you have a welder who's been around but he's waiting, or his arcing time is only a couple of minutes a day, then you know that the utility of the person is not fully there. So what are the steps to consider? We need to know why you want to do the IoT. So we will discuss that next as to why particularly you want to do a particular implementation. So you need to collect data and analyze that data based on the purpose of your IoT. So, and then we'll use relevant data points and sensors to that effect. Second is number of equipments that you want to connect to the IoT. So you want a single machine, you have multiple machines, you have single location, you have multiple locations. How close are the equipments to each other? Third is the network infrastructure required. So whether you want to use USB, LAN, RS485, Wi-Fi or GSM, or you want to go, if you're having multiple stations, you want to connect them using LAN, wireless or GSM. And fourth is the server considerations, whether you want the data on a cloud, so you can access it through a remote server, or your data is very sensitive and you would want it installed on the PC within your premise itself. So these are the considerations for that. So first step, you have to always begin with the end in mind. You must have your objective clear. So there are two types of industries which are critical to applications. That means nuclear, medical, etc., where human lives are at stake, and they are also very, very concerned about the metallurgy. So welding quality and process monitoring play a vital role there. Another is mass production, where, you know, although welding quality plays a role, but cost of production also plays a very, very major role. So cost and productivity monitoring is very high. So consider auto ancillaries as one of them, or furniture manufacturers like another one of them, where you would want to know the total cost of production, more importantly. So based on what you chose, quality or cost, what would you capture? So to process quality, you want to know exact parameters: welding current, welding voltage, gas flow, wire speed, and job temperature. You can also have other parameters such as wire diameter, filler material content, and etc. on that, right? Not to mention welder qualification also qualifies as a quality process parameter. And what is there that is on the cost side? You have arc on time, heat input. These are productivity measures. Weld deposit, total gas consumed, total consumable consumed, that is the wire. And then TPM data, that is total productivity management data, that can take into consideration factors such as activities which were, you know, productive and non-productive, and how much non-productive activity which was done was necessary and was not necessary. So you can capture that data. Now, based on these parameters, we will choose particular sensors which will help you capture the particular data. So we have current transducers to capture current. We call them CTs. Then you have shunts which capture voltage. So they can show you how many volts was there during welding. Then you have gas flow switches which capture the flow of the gas in LPM. Then you have liters per minute. Then you have mass flow controllers which help you capture the total amount of gas that has flown through, which would be in kgs, right? The actual gas consumed in kgs or liters. Then for temperature, you would have optical pyrometers or K-type thermocouples, which can be used. And for motion, that is the rotary or linear motion, you would use encoders or motion detectors to give you the speed that you wanted to know. Right? Here is a sample example of a data monitoring system that you can see. This has a voltage, welding current. It shows you wire feed rate in meters per minute. It shows you wire deposition in grams, and it shows you gas flow in liters per minute. Below that, it is showing you arc on time and arc off time. So arc on time, arc on time shows you how many hours was the welding machine on for welding, and arc off time tells you how many hours was the machine idle for. So you powered on the machine but not used it for 22 minutes, but you've not welded since yet. So this is the kind of just a screen that it shows. Now, this is what a CT looks like. A CT is a current transducer. You put the bus bar through the CT. This is a split open CT. So you can put it across the welding cable or the power cable. You can also use a bus bar through it, a copper bus bar. And it captures through magnetic interference. It captures the kind of current that is flowing through the cable. And then it translates that into a 0 to 15 plus minus 15 to plus 15 signal. And this signal is then interpreted by the microcontroller or PLC to find out the voltage at current level that you are welding at. The CTs have a rating. So if you are welding for 400 amps, you can use a 400 amp CT. It will go from 0 to 400. You can have 600 amp CT, which go from 0 to 600. You can have a 1000 amp CT, which goes up to 1000 amps. And then you can use 2000 amps for between 1000 and 2000 amps. So there are CTs available, and these are either split core or hollow core. So you can push a conductor through the same. On the right hand side, you see a standard shunt. If you connect the wires across here and the terminals to a cable, it will tell you the voltage drop between the two. So it will tell you if the voltage was how much you wanted. Even that is used to measure the voltage. Now, gas flow, you all would have seen a typical gas flow tube on top of your cylinder, which is a transparent tube with a floating ball, which shows you how many liters per minute, but that doesn't give you digital data. So digital switches come something like this. You have an in and out. If you put the gas in and gas out, it will show you the flow through it at a particular LPM. You see green and red. You can set the value that you want. If it goes above or beyond that value, it will become a red indication that you are below or you are out of range. Then you have a needle adjuster on this digital flow meter, which will allow you to adjust the flow as well. You can adjust the flow from here to get the right flow. So not only measure, but control as well. So this is called a digital flow switch. And this gives you output in terms of 0 to 10 volts, 4 to 20 milliamps, or you can get ones with a LAN cable as well. It will give you a 485 signal and you can access the parameters within it. Then there is something called the mass flow controller. The mass flow controller has this kind of a configuration where the gas in comes, you have a bypass which allows you to push the level up. This connects to a bridging circuit, an amplifying and a correction circuit, which then gives you a display of 4 to 20 or 0 to 5 volts. And then you can set how much you want the flow through it, and it will do a comparison, open the proportionate valve accordingly. And so that gives you a flow as per what you wanted. So this is called a mass flow controller. It allows you to control the pressure and flow through the system. At the same time, it can capture and collect how much total amount of gas was consumed, and it can sense this data and share it with you over 4 to 20 milliamps or over a LAN interface of Ethernet. Temperatures, there are K-type thermocouples. So this is a typical K-type thermocouple. You short the positive negative alum onto the job itself, and this acts as a junction. It measures the temperature through this, and this is connected to an isolator and then to the K-type reader, which will tell you what was the temperature at the joint. Then you have nichrome wires that you see here. You have optical pyrometers, which can be single lens, double lens, or it can give you the actual temperature reading. And this reading can be shared with you from a interface 0 to 10 volts, 4 to 20 milliamps, or any other protocol. Optical pyrometers also come with settings for emissivity because it can differentiate the temperature based on the emissivity of the part. So sometimes it can give you a slightly false reading. So they have to set the mode and the emissivity to give you the clear recordings. Then there is the handheld temperature guns. Again, these will give you instant readings, but they may not be able to connect them to transmit the data to a automation system. So these are handheld devices. These are the ones that relay it and can be captured by an automation system. This is an encoder or a motion detector. So if you have any motor or a moving assembly, if you mount the shaft through this encoder, it will have a light source. It will rotate this code disk as per the movement of your motor shaft. As many times as it rotates, this will generate pulses because of these light source will pass through this perforated sheet. And this has a particular, every RPM will give you a particular number of pulses. Those pulses are then measured by the electronic board, and it can tell you what is the speed at which the motor is moving. So with this speed and time inference, you can measure distance. You can measure the rotational speed and other needed data on motors. Having captured the data from the welding current voltage and the motor, now comes the welder. So how do you capture the data of a welder? You can allow the welder to log in using a username password. You can allow the welder to use fingerprints on the machine itself, which will be like a fingerprint reader. You can use RFID cards. So you all have used these, cards to enter or to register your entry. Those are RFID cards, or near field cards, NFC cards. So you see these smart cards that you have now on your in your wallet, which you use to pay your ATM cards. They have a smart chip. They are all NFC, near field. So when you place it closer to the sensing device, it will record your data and tell you what is happening. Now, out of these, if you're using it on a shop floor, you can imagine what will happen to an HMI based system. If you use an HMI based system to enter the data, log in as a user, the operator may have dirty hands and can spoil that very quickly. The other way around is that if you have fingerprint readers, then there is another challenge that fingerprint may not work very easily because of the fingerprints may not work very easily because of the repetition of the finger type, dirty fingers. So if they have grease on the hand or if they have something else, it may not allow them to weld very easily. The third is the RFID readers are, as we discussed, easy to use. NFC cards are easy to use. So if there is a shop floor, fingerprints are not so much used, but other than that, the other three can be used very effectively. Now, we are going to get into the TPM data next. So we can stop here and we can take the rest of it tomorrow. If there are any questions, I can take them now, because then it will be a disc break between now and later. Is that all right? Because I believe the time is still 9 o'clock. So if there are any questions, we can take it for the next 15 minutes or so. Or if you want me to continue a little more, I can do that right now.
Sure, sir, as convenient for you. We have certain questions in the chat box at
Right.
present.
Right.
Sir, one question is suggest a software for IoT based welding.
Okay. So software for IoT based welding is basically not a very correct question per se. If you are using IoT to measure data, then that data will be extracted, and whoever has given you that data will also extract an answer, have a software which understands that data and analyze it for you. So what is important is to know what kind of data that you want to collect. So if you are asking me whether there's an IoT platform or a readily available gateway, there are many that you can use, and they will transfer the data on the many standard protocols, and they can give you that data through MQTT, and you can read that data. So there is JSON files or there is MQTT, which allows you to transfer the data and take it over any standard gateway. Okay.
Okay, thank you, sir. And sir, one more question is there. Sir, is it possible to monitor real-time weld metallurgy through IoT-enabled sensors? And the same person has put it like this, or can IoT devices monitor the changes in the microstructure during the welding processes in real time?
So if you look at it, if you want to, when the welding is happening, you can measure the temperature, the current, and the voltage, or you can monitor the weld pool, how it is behaving. But metallurgy will only come into play once it's cooled down. So the molten stage itself, you can measure at that time, but real time, if you look at it, once it's cooled down and it has allowed it to settle, you will be able to see this further. There is another analysis to this is if you had a couple of plates that you've already welded, or I would put this as an export system. If you welded a particular metal with a particular parameter, and you know that the microstructure has not come right because of XYZ reasons, then when you are welding, during welding, if such an occurrence happens, then the IoT device can allow you to stop welding at that stage and not let that happen, or alert you at that stage. There is also some research happening with welding cameras, thermal cameras especially, for submerged arc welding where it is not visually seen. That how temperature profile changes, and that can be analyzed through AI and then later given that, okay, this was good, this was bad, or this may have some failure because of the past repeatability in the past of such systems.
Okay, noted, sir. Sir, one more question is how digital twinning works in welding.
So digital twinning, basically you want to mimic something that's happening real time. So cobots are something that are being used right now where the operator can take a cobot instead of a robot. He can press learn, move his arm as he would weld, and release. And the cobot would then follow that path repeatedly. So this is one way where digital twinning works. Other is that if you have everything set up correctly, you practice it and you set it up, then this is very useful for remote repairs. So one of the projects that we did for remote repair in a nuclear plant, we had to simulate a welding. We had to actually do a welding 800 millimeters inside a wall with only 50 millimeter clearance around. Now, when you are trying to do something like this, you cannot do it the first time on the job. We had 200 odd setups done beforehand, and we had set the parameters and taken other things that were required to set it right. Having done this 200 times, put in those parameters and those data into the AI and the automation in welding, when the final joint was to be done, the system already knew what, when it was progressing at each angle that it changed, what parameters it had to weld at. And so when it did that in terms of welding autonomously, it was done in remote repair where the operator is not there. You cannot see anything. The operator is sitting right at the other end and you only can press start or stop. And this is how digital twinning works in welding.
Very remarkable, sir. Sir, one more question is, please suggest welding simulation software.
So Arunaji, there are two different modes, right? Three different modes for welding simulation. One is called the standard simulation, which works like a gamification. So which is in AR, augmented reality, where you wear a set of glasses or a set of helmet, and you see pipes or plates which have got markings on it. So as soon as you wear it and you go into augmented reality, you will see the real image in front of you, the thickness that you chose, the kind of structure that you chose, the material you chose. You will see that in front of you instead of the plastic plates. Now this is called augmented reality, where you see it very close to reality in 3D, and you're still doing it in live in the 3D mode because the parts are real in front of you in plastic. But the AI does it in augmented way for you, so it's called augmented reality. The other software simulation comes, which is called VR, which is virtual reality, in which you select the particular thickness, the material and everything, and it gives you an image of that. And then you take a real torch and you move it along the lines as if you would, and it will capture the data and simulate the welding for you. This is what VR does. So there are different, not only softwares, but software plus hardware available for VR and AR. I can suggest a few names if you want. So there is something called the SimBot. I'll type it down. One is SimBot. One is called Skillberry. They made a simulator called Velu. So IIT also developed one, I believe, which was called Velu earlier. And these are one is, and then there is one which is called Soldomatic. I believe Professor Badeka recently had one of the demonstrations on Soldomatic. I saw one of his posts.
Yes,
So
yes.
Soldomatic is a virtual reality, augmented reality. Skillberry is a virtual reality, and SimBot gives you a combination of virtual and augmented reality. So these are ones that are available today in the market. Sure, somebody wants various sensing system catalogs. Later, maybe you can send a mail to me and I can send you the catalogs or the part numbers that you can look up for the sensors.
Sir, my question, that you are talking about the IoT connections with the machines,
Right.
which we can reduce the real-time problems. You had also quoted the case study. So whether it is the IoT connectivity is going to reduce the lean manufacturing, or it is going to do the Pokayaki alone?
So Pokayoke goes hand in hand if you have a fully integrated system, right? So there are
Yes.
systems, for example, in your lab, you already have a welding machine. Now to have IoT, you may not want to invest that much money. So let us understand this, that in an industry, somebody has already got maybe 100 machines working on the shop floor. Very difficult for them to decide to throw away 100 machines and now put new 100 machines with IoT in it. The cost implication is very high. So in such cases, you can start off with the additional IoT. That means only measure and monitor, okay, and report, which will connect onto an existing welding machine, measure the data, analyze for you, and give you a report. But you can also have a new machine which is fully integrated with IoT, in which Pokayoke is a part of it, because it will not allow you to do something wrong. So Pokayoke means
Yes. If something is error, and they will not make you to move to the next process at all. They will going on peeping
correct.
or something.
Here in Pokayoke, in terms of welding will be, if I know that the welding parameter is between 100 to 125 amps, I will not allow it to go to 80 or 150. So when I select the WPS, if I do Pokayoke, if I have a fully integrated system, Pokayoke is inbuilt how? I said, I am the welder. This is the job I'm going to weld. The WPS came directly from the server. When it came from the server, it already wrote to the machine. It spoke to the machine and it told the machine, this is the welding range you have to work in. Now the operator has no control beyond the welding range. Okay. So
Yes, sir.
in very simple terms, if you are driving a car and there is a zone which says this is a school zone, you cannot drive beyond 40, right? The minute your car saw a school zone symbol, the car will bring down the top speed to 40.
Hmm.
If the car
Right.
does that, then there is Pokayoke in place. Now, same thing is with welding machines. If the welding machine can decide this is the WPS, so I cannot allow you to go beyond that, then Pokayoke is already in place. Correct?
But what about the lean structures when we are having it, sir? Then, if you are finding out with the data that these are all some of the processes which can be eliminated through that this error processing or some extra steps we are doing it, we can
Correct.
curtail those and we can directly go to the next process, and so that we can also do the lean manufacturing, and which is possible through these IoT devices, sir,
It is
while you're
possible.
collecting data.
You can collect the data, but so I'll give you one example of this. We did a project for a company called L&T in Kanchipuram, where they have about 47 to 50 machines which work on the yard, and they have more than 100 welders. So every morning, the supervisor the day before has allocated a task to each welder and uploaded onto the system. Now, all the 47 machines are the same capacity machines, right? Now the welder goes in the morning. He takes his card, his attendance card. He swipes his attendance. When he's swiping his attendance, the supervisors, the data he had given that the welder is supposed to do this job gets loaded onto the card. Then he goes to the store and he gives his card, and the storekeeper swipes the card. It tells the storekeeper what consumable this fellow is supposed to take today. Storekeeper will only issue them that consumable. Correct? Now he goes, takes this consumable and goes to the job he is supposed to weld on, and he swipes his card on the welding machine. Now the welding machine records this welder has logged onto this machine, and the server, the card has already told him this is the welding parameters he's supposed to weld at. So now he's restricted to that parameters. He doesn't need to set anything. He only needs to start welding. So here the entire process of lean manufacturing came into place. He doesn't have to waste time in terms of identifying what material I have to issue from the store. The storekeeper doesn't need to find how much to give, how much to take back. They directly got the data throughout the system, and then the system became lean. In welding, you cannot bypass the first pass and go on to the third pass of welding. You have to go through the process that exists. But you can streamline the processes where the time is being wasted. Is that
Yes, sir.
somewhat clear?
Clear, sir.
Yeah. Okay. There is one question by Dr. Sumit Saini. In future, will computers replace humans from welding? Future is collaborative. It is not completely autogenous. So it was very difficult for us to believe ages ago that a car can drive itself to wherever you want to go. But today that is a reality, right? In US and Tesla and others have autonomous cars. You sit in the car, you tell them where you want to go. It will navigate traffic, everything, and it will take you there safely. So computers or automation will do the welding. It can be completely automated as well. But then there is a question of viability or cost. It will not always be cost effective to get that done. So there'll be a lot of work which cannot be cheaply done using full automation. So those places humans cannot be replaced. And that is not necessarily, it is non-critical. It can be critical also. But humans will be required to program. Humans will be required to observe. Humans will be required to verify what has been done is correct. At the end of the day, it is being done for a human, right? So human intervention will be required. Maybe the fatigue that a human endures while doing welding will be greatly reduced. So this is where I see in the future, it will be collaborative. It may not be zero because of viability issues and also because of other possibilities.
So the health hazards and hazardous materials or the emissions which is happening while doing the welding can be replaced with the robots and with other tools, sir.
Yes, yes, of course. So like in operations today, you see that there is remote operations happening, right? You are sitting in one cabin. So there is a customer in which the operator sits in a AC cabin, the welder. He sits in a AC cabin on his IoT station and he's operating 3 welding machines at the same time. He is observing, he is giving commands for what is to be done, but the welding is being done through automation. So that is possible, yes. Okay. Is it possible to develop mechanism which can convert current machines into into industry IoT machines? Yes, Dr. Amit, that is possible. There are add-on patches that we can use. As I said, there are 3 phases. Phase 1 is to collect the data and analyze. Phase 2 is to correlate that to WPS. So till here we can do on any existing setup. Stage 3, which is where you want to control at that time with different customer bases or different machines, communication may be different. So that may or may not be possible. But first 2 stages is definitely possible. And there are like we have a solution to do that for any machine. Where she is asking which software are used in welding training in AR VR technology for training purposes of welding operator. The software is usually custom built and it's done using one of the standard softwares, but most of them will have a customized software to their platform. So Soldomatic will have to their platform and the AR guys, virtual reality guys will have to their platform. They are largely simulation softwares and created in 3D. So they have a lot of backend calculations. So when you say plate size, plate thickness, material, it brings in those characteristics. And then when you move your hand, it has to sense the gyrometrics will sense your hand movement, angle, and it will determine the weld quality on that basis. Okay. And I hope that answers your question. And I see one more question says, how does IoT integrate with data analytics in welding for better scalability? So better scalability is very easy. Suppose if you integrate IoT with basic welding machines and you capture the data, then you know how much is the arc on time, etc. Now, when you are scaling up and say, I want to expand my factory, you know whether you can add another shift. If your utilization is low in the first 2 shifts, then the equipment can be used there on the third shift. This answers, I think, tomorrow when I take the session and I'll show you some live data, it will answer it better when I show you 47 machines working, what is the graph, how each machine's utility is shown. Then you can, as an operator or as a supervisor, you know what needs to be done and what needs to be avoided. Professor Prashant, how to assess the IoT capabilities of the present machine? If you have a present machine, you don't need to assess any. If there is no IoT in it, you don't need to assess anything. All sensors can be added externally and captured the data. That is the beauty of it. You can capture the data of any process and then report it back to the station without disturbing the present process or the equipment. All right. So any more questions or we can take this up further tomorrow? Humans will always work, always work, always work. There is no other alternative. We need to work. If we don't work, we will not know what to do. There was a very beautiful movie. It was an animation movie long back called Eva. And in this, a robot is cleaning the earth, and that robot gets tagged away to another planet. And on that planet, humans are living on spaceships. And when they find something green, the spaceship is supposed to take them there to identify, okay, there is a Earth-like, planet somewhere. And when they show the inside of the spaceship, because humans are no longer doing anything, they are all lying around, walking, and you could see the sizes of the humans have changed. They are very big, fat, and it shows that if we just keep using Wally is the right movie, correct? Thank you so much, Arun. I forgot the name. And this it shows how humans, if they don't work, it is not going to give you the right results that you want. Correct. Wally is the name of the movie. There are two more questions. Does IoT contribute to battery management systems in EV? It can contribute to any process systems. In EVs, it's a must because you want to know the battery life, you want to know the charge life, you want to see how often it's being used. So of course it is there in battery management systems, but IoT is analyzing data in any process. So if you have a process, it can measure some data, you can analyze it, then you can see it in a different light. And IoT is the last mile bridge where it takes it over the internet and makes it accessible to you anywhere. Industry 5.0 is a collaboration between humans and machines. It can be completely robotics. It's right now still collaborative. There are completely automated plants as well, wherein parts identification, placement, welding, exit, packing, and loading all happens through automation. But again, as I said, viability of cost becomes a big question. Okay, so I think that's it for today. If there are any more questions, I'm happy to take. Otherwise, we'll continue tomorrow.
I guess, sir, all the questions have been asked. So I would like to thank you on behalf of all the participants to share your expertise with us today. And yes, we are very eager to hear you again in your next session.
Thank you. Thank you so much. It was a pleasure and nice to see good set of questions coming in. So I'll see you all tomorrow, same time.
Sure, sir. Dr. Vishwesh, sir?
Yeah. So Nimish Roy, thank you very much for sparing your valuable time.
Thank
And
you.
it was really a wonderful session, making the audience aware about the Industry 4.0 and its integration, especially with welding operation. Thank you once again.
Thank you. Thank you, everyone. Thank you. Have a great night.
Thank you.
Thank you, sir.
Thank you, Manoj.
So we would like to conclude for today's session. I would like to thank each of the speakers, Dr. Harshit Dave sir and Mr. Nimesh Chunai sir, for their valuable time, sparing their valuable time for this faculty development program and giving their expertise to all the delegates. Now, this is really great, sir, because we have another sessions tomorrow of yours, sir. And I am looking forward, and all the delegates are looking forward to hear you again, sir.
Thank you so much.
So thank you once again, and thank you all the participants for your active participation. And we'll meet tomorrow at 6 p.m. for another set of insightful sessions. So thank you once again, and good night.
Thank you. Good night. Thank you very much.
Good night,
Thank you.
sir. Good night, all. Good night.
Thank you. Thank you, sir.